Good morning, everyone. Let's get started. In the previous class, we were discussing typical sets and their geometry, and we looked and basically we studied the case where you have joint binary sources, in particular where X is drawn IID Bernoulli Q, and it is passed through a BSC to get another Y, right? And we saw that this has an interpretation in terms of Hamming balls and Hamming shells. If you look at very large enough n, then a Bernoulli sequence xn, a Bernoulli Q sequence xn is going to lie within a thin shell of Hamming radius roughly equal to n times q. Right? And now if you pass this through a BSCP, then the received Y is going to lie within a thin shell of Hamming distance NP from Xn. And for Xn and Yn to be jointly typical, the intersection is going to be basically this red region over here. It is the intersection of this shell with another shell of Hamming radius, roughly n times p star q, where p star q is p into 1 minus q plus q into 1 minus p. Right, so this was again by way of intuition. This is just to visualize what these typical sets look like and what exactly happens in high dimensions. So later on, we also looked at the conditional typicality lemma, which says that if you take an xn which is typical, which is epsilon prime typical, and you pass xn through any DMC, and to get some yn at the output, then xn yn is also going to be jointly epsilon typical, where epsilon
Sir?
is greater than epsilon prime. Yes.
Sir? Sir, are you presenting any screen? Your screen? Like, I'm not able to see your screen.
Is it? What about the others? Are you able to see the screen?
Yes, sir. It is
And now
visual
it is
purpose.
coming, sir. Now it is coming, sir.
Okay, so probably some kind of
Now
network issue.
yeah. So, sorry, sir.
Yeah. All right. No worries. I can. Yeah. So you can see it now, right? You
Yes,
can
sir,
see
I
the
can see
screen
now.
on the conditional typicality lemma, right?
Yeah. I can see it now.
Okay.
Yeah.
All right.
Sorry for interrupting, sir.
No worries. Yeah. Okay. So as I was saying, if you look at any typical epsilon prime typical xn, and you pass this through a DMC to get yn, then xn and yn are also going to be jointly typical, but they're going to be jointly epsilon typical for some epsilon greater than 0. So the slack that you need to give, the epsilon that you need to choose, should be larger than epsilon prime for them to be jointly typical. Okay, so we'll explore these ideas a little further in this class. So far we've seen that you're fixing a particular distribution. For a particular distribution, you define the typical set, and then you say that if you actually draw random sequences from this distribution, then they're going to lie in the typical set with high probability. Right? And the size of the typical set is typically much smaller than the size of the entire space. So it's actually a very small set, relatively a small set. It's of exponential size, but much smaller than the size of the entire space. And basically, most of the probability is concentrated in this small set. Now, in this class, we'll explore what happens if you draw the sequences from a slightly different distribution. So maybe you look at the typical set corresponding to a particular pxy. Let us say that I draw a sequence xn, yn, not from pxy, but instead maybe qxy. Okay, and in this case, what happens? What is the probability that the sequence will be typical? We'll see that this probability is actually vanishingly small, and we'll try to characterize how small the probability can be. Because ultimately, this is what will help us in deriving upper bounds on the probability of error for various channels and for various sources. Okay, so before we proceed, are there any questions? Any questions? Right. So I hope you've already sort of worked through the proof of the conditional typicality lemma yourself. I did give a proof. I didn't complete all the steps, but hopefully the remaining part is it's just simplification. So you should be hopefully be able to do it yourself. Okay, so now we'll see another result which is called the joint typicality lemma, and this will be a key step in proving an upper bound on the probability of error for the channel coding theorem, for the achievability part of the channel coding theorem. And it basically says the following. So it's a more specific or specific form of what I just mentioned. So suppose you look at three random variables, okay, x, y, and z. All right, you take three random variables, and you take any x n, y n. Take any two sequences xn and yn, and we know that if we draw zn according to p z given xy, IID pz given xy, then if xn and yn are typical, then xn, y, and zn are also going to be jointly typical. But now, what if zn is not drawn according to pz given xy, but instead according to pz given x? Okay, so basically z is drawn independently of y. It's dependent on x but independent of y. Okay, you fix two sequences xn, yn, and you randomly pick a zn dependent on x but independent of y. Okay, and the distribution you use is pz given x, IID pz given x. Then the question is, what is the probability that the triple xn, yn, zn is going to be epsilon typical? Okay, the claim is no matter how you choose xn, yn, whether they're typical or whether they're atypical, the probability that these three sequences xn, yn, zn are going to be jointly epsilon typical is vanishing in n, and in particular, it is this probability is less than or equal to 2 raised to minus n times the mutual information between y and z given x. Okay. And one interpretation of this part of the joint typicality lemma is the following. So in the channel coding theorem, we're interested in finding out what is the probability that Zn maybe. So in the channel coding theorem, the notation here is a little bit different, but consider the problem where you transmit a yn through a DMC, and at the output of the DMC you see Zn. Okay, and xn is something which is some kind of shared information or whatever. So in the channel coding theorem, we'll not really use xn, but we'll only have yn and zn for the channel coding theorem for the point-to-point case. Now, if I have the input as yn and the output as zn, now there are different zns that could occur, or different yns corresponding to different code words, right? Now, we'll see that if zn is obtained by passing the true code word through a DMC, then the true code word and the received sequence zn are going to be jointly typical with high probability. Now, what about the other code words? Can Zn be jointly typical with any of the other code words? And we'll see that that cannot happen. And in fact, the probability that Zn is jointly typical with some other yn is precisely bounded by this particular quantity. Now we'll discuss this in more detail when I go over the proof of the channel coding theorem, but it's helpful to have this intuition in mind right away. So yn is some sequence, and zn is drawn independently of yn. Okay, and we want to know what is the probability that yn and zn are jointly typical. Or in this case, when you have another xn, what is the probability that xn, yn, zn are jointly typical? And this probability is very small. It is 2 to the minus n times the mutual information between yz given x. All right. So this is one part of what is called the joint typicality lemma. It gives an upper bound on the probability of the three sequences being jointly typical. Now, in some cases, we'll also want a lower bound for the probability that they're jointly typical. So similarly, if xn and yn are indeed jointly typical, are jointly typical, so they're drawn from t epsilon prime n of pxy, and then you draw zn from according to the distribution pz given x of pz given x given xn. So zn is again drawn dependent on xn, but independently of yn. But xn and yn are jointly typical. Okay, so in this case, xn, yn, and zn are jointly typical with a certain probability. So you can derive a lower bound, and this lower bound, at least in the first order of the exponent, corresponds to the upper bound that we have over here. So for any epsilon greater than epsilon prime, the probability that xn, yn, zn are jointly typical is lower bounded by 2 to the minus n times the mutual information between yz given x. Okay. So let's see a proof of this particular statement. Now to use
Sir,
yes.
Sorry to interrupt.
Yes, please.
In the first one, we are not saying xn and yn are jointly typical, right? In the second statement, we are considering they are jointly typical.
Correct, correct. So to prove an upper bound, we need to make absolutely no assumptions on xn and yn. The upper bound is valid if whether they are jointly typical or not. So if xn and yn are jointly typical, the upper bound still holds. If they're not jointly typical, the upper bound still holds. But when we want to derive a lower bound, then we have to have the assumption that xn and yn are jointly typical. If they're not jointly typical, then you don't have this particular lower bound. But if they are jointly typical, then this holds.
Okay, sir.
Any other questions?
Sir, sir, you are on mute.
Yeah. Okay. I'm audible now.
Yes, sir.
Okay. Thanks. Okay. So what we want to know is that so now we are fixing xn and yn, any fixed sequences xn, yn, and zn is drawn according to is drawn IID pz given xi. And we want to know what is the probability that these are jointly typical. All right. So this is basically, so you sum over all possible Zn such that xn, yn, Zn is in the typical set okay, and times the probability of this Zn. So this Zn is drawn according to Pz given x, going from 1 through n of Pzi given xi. Okay, so you want to know what this particular probability is, right? Or basically we want an upper bound. So for this, we'll first use the fact that we're summing over only elements which are in the typical set. Okay, and we're drawing Zn from the probability Pz given x. Now, if you're only looking at sequences in the so here basically we have sequences in the conditional typical set. So here Zn belongs to the conditional typical set, which is the epsilon n of p xz given a particular xn. So this is the conditional typical set, and for the conditional typical set, the probability of any Zn in this set is always going to be roughly 2 to the minus n times h of z given x times 1 minus epsilon. So this is an upper bound. So it's going to be, so the probability of Zn, z given x, Zn given xn is always going to be less than or equal to this, and this follows from properties of the conditional typical set. Okay, so we have that. So therefore, this quantity is always less than or equal to the summation overall Zn in Zn such that xn yn Zn is in the joint typical set the epsilon n. So all these sequences are jointly typical, right? 2 to the minus n times h of z given x times 1 minus epsilon. Okay, so this now here we're actually drawing according to Pz given x. So the Zn that is drawn from here corresponds to the conditional typical set T epsilon n of Pxz given xn. Whereas here we're looking at all possible sequences in a slightly different typical set. In this case, the Zns that we are summing over, this corresponds to T epsilon n of Pxyz given ynzn. All right, so this, but the size of this particular typical set, T epsilon n of Pxyz given yn zn, this is going to be less than or equal to 2 raised to minus n times. So note that we're drawing, sorry, this is given xn and yn. So we're fixing xn and yn, and you're looking at the typical set. So the set of all sequences Zn which are jointly typical with respect to x and y. So this is going to be less than or equal to 2 raised to n times h of z given xy. So roughly 2 raised to n times h of z given xy. So there'll be a plus times 1 plus epsilon. So this the term within the summation anyway is independent of the particular z. So we can just take it outside. We have 2 raised to minus n times h of z given x times 1 minus epsilon. This times the size of t epsilon n of pxyz of yn xn, which is of course upper bounded by, so this term is as it is, 2n minus h of z given x times 1 minus epsilon times 2 raised to n times h of z given xy times 1 plus epsilon. So if I just simplify the exponent, I get 2 to the minus n times h of z given x minus h of z given xy plus epsilon h of z given x plus epsilon times h of z given xy. Minus h of z given xy. So this is just 2 to the minus n times the mutual information between z and y given x. This term also simplifies to plus epsilon times the mutual information between z and y given x. So this is just 1 plus epsilon. Let me see. Oops, sorry. I guess this should have been minus. So this is minus and this is going to be plus. So the probability of error is, or the probability that these three are going to be jointly epsilon typical is upper bounded by 2 raised to minus n times the mutual information between z and y given x times 1 minus epsilon. Okay, so let's go through this perhaps once again. We want to know what is the probability for a fixed xn, yn. We want to know what is the probability that xn, yn, zn are jointly typical. All right, but we are drawing zn from according to p z given x. Right, so this probability is the summation over all zn which are jointly typical with respect to x and y times the probability of drawing that particular set, which is pz given x. Right, but if it is conditionally typical, then this probability is upper bounded by 2 raised to minus n times h of z given x times 1 minus epsilon, because we're drawing according to pz given x and not according to pz given xy. If we are drawing according to pz given xy, then this quantity would have been 2 raised to minus n times h of z given xy. So we have a 2 raised to minus n times h of z given x over here, and we're summing over all possible zn which are conditionally typical with respect to y and z. So if we just take this out, then we get this times the size of this typical set, the conditional typical set of z given xn and yn. But we've already seen what is the size of the conditional typical set. It is less than or equal to 2 raised to minus n times h of z given xy times 1 plus epsilon. right? And this basically simplifies to 2 raised to minus n times the mutual information between z and y given x times 1 minus epsilon. All right. So maybe what sometimes can get a little tricky is to know what these probabilities can be. So I've just said that this probability is 2 to the minus n times h of z given x. Some things over here are 2 to the n times h of z given xy, and so on. You have to be a little careful, but there's an easy trick to remember what the right exponent should be. Right? So whenever you're drawing something according to, say, px given z of something, or let's say I have p, say, xy given wz, if I'm drawing something according to this for a particular wn zn, then the probability pxn yn given wn zn for any jointly typical xn yn is always going to be less than or equal to 2 to the minus n times the entropy of xy given wz. So roughly, so it's going to be 2 to the minus n times h of xy given wz times whatever 1 minus epsilon. All right. So whenever you have xy given wz, it's always going to be 2 to the minus n times h of xy given wz. This upper bound always holds. If in addition wn and zn are jointly typical, then you'll also have a lower bound. This will be 2 to the minus n times h of xy given wz times 1 plus epsilon. So this upper bound will always hold. And if you want to know what is the size of a particular typical set, the size of a typical set, say px y, so this size is going to be always less than or equal to, no matter what n is, this is always going to be less than or equal to 2 to the n times h of xy. Right? And for sufficiently large n, this is going to be greater than or equal to plus 1 plus epsilon. This is going to be greater than or equal to 2 to the n times h of xy times 1 minus epsilon. And the size of conditional typical sets will always have conditional entropies in the exponent. So if you want to know what is the number of, so this is the number of xy pairs which are jointly epsilon typical. Now if you want to know what are the number of y pairs which are jointly typical with respect to a particular xn, so this is the number of sequences yn which are typical to with respect to a particular xn. This is going to be at most 2 to the plus n times h of y given x. So you're drawing sequences yn for corresponding to a particular xn. So this will be 2 to the n times h of y given x times 1 plus epsilon. Now if xn is typical and n is sufficiently large, then you'll also have a lower bound, a very similar lower bound, which is 2 raised to n times h of y given x times 1 minus epsilon. So whenever you have conditioning over here, whenever you're conditioning with respect to a particular xn or a particular wn or a zn, then you'll have an entropy of y given x corresponding to those variables with respect to which you're conditioning, and and whatever you're drawing randomly or the set of sequences that you're considering will appear over here. Right? So that's probably an easy way to remember what the right exponents should be. But of course, these epsilons and deltas could vary depending on what is the exact quantity that you're looking at. All right, and that is basically what we will be using in many of our calculations. All right, any questions?
Sir?
Yes, Aman, go ahead.
Okay.
So, sir, to summarize the steps, first, what we are doing, we are just taking, we are calculating the probability that x, y, z are jointly typical. So now what we are doing is we are just fixing y, like we are summing over all yn, and then we are taking that. We are choosing those z, those are jointly typical with x. Now after that, what we are doing that we are calculating now. After that, what we are doing, like we are taking all yn given x, right, sir? In the
No.
and then we are
So you're fixing a particular x and y upfront. You fix any x and y,
okay.
and you want to know what is the probability that xn, yn, and zn are all jointly typical. All three of them are jointly typical. But
Yeah,
I'm drawing zn independently of yn.
correct.
So zn is dependent on this particular xn that I'm choosing, but it's independently drawn but it's independent of y. And I want to know, even though I'm drawing it independently of y, what is the probability that all three are going to be jointly typical?
Okay, got it.
Okay. Any other questions?
In the just before the proof, the two statements which we have written.
Correct.
Can you just scroll up, sir? I think there is some
Okay.
in the
This-
first one.
Correct.
Yeah, in the first one, it is y 2 power minus n y given z given x y comma. But here it is z y given x.
That's the same, right? So it's symmetric in y and z, right?
Symmetric in y and z.
So the mutual information between x and y is the same as the mutual information between y and x.
Yes, okay, information.
Right.
Yes, property.
So whether it's whatever I z y or I y z, it's basically the same thing.
Okay.
Okay. Any other questions? Okay, so let's try to quickly do the lower bound as well, and you will help me with that. So let's prove part 2. So now what am I doing? I have xn and yn, which I know are already typical. Okay, so they are in T epsilon prime n of Pxy. So they are jointly typical, and I'm drawing Zn according to P z given x. So z given x, so whatever it's IID Pz given x, this given a particular xn. So Zn is still drawn independently of yn, but xn and yn are additionally they are jointly typical. Now once again I want to know what is the probability that all three of them are jointly typical. And yn, zn, these are jointly typical, but they're epsilon jointly typical. P, x, y, z. Right? So once again, this is just the summation over all sequences zn, which are such that xn, yn, zn. So I'm summing over all possible zn, which are typical with respect to yn and xn. X, y, z times the probability of occurrence of this particular zn. So pz given x of zn given xn. Okay, so remember now that I want a lower bound. Okay, so first I know that xn is typical, and xn is, so since xn and yn are jointly epsilon prime typical, xn is also epsilon prime typical with respect to px. So what can you say about, do we have a lower bound on this particular probability? What will that be?
So it will be at least inside the summation it will be 2 to the power minus n h given z plus epsilon.
H of?
H of z given x.
Correct. Z given
plus
x.
Epsilon.
So times it's going to be 1 minus, 1 plus epsilon.
1 plus.
Right, and note that in doing this we're using the conditional typicality lemma that we saw in the previous class. So you have an xn, you pass it through a DMC, or basically you draw yn according to py given x. So the probability that these two are jointly typical is vanishing in n, and in particular the probability of occurrence of this particular xn yn, it will be 2 to the minus n times. So somewhere over here, yeah. So you can show that this probability will be at least 2 to the minus n times h of z given x times 1 plus epsilon, and this holds for large enough n. For large enough n. Okay, so we have this, and we can take this outside. Right, so this will be equal to 2 to the minus n times h of z given x times 1 plus epsilon times, now what is this going to be? It's going to be summation of 1, but you're summing over all zn, which are jointly typical with respect to xn and yn. So you just get the size of the typical set of p x, y, z given xn and yn, right? So now do we have a lower bound for this size? So what will this be? 2 to the n times?
Sir, I couldn't understand it's like typical set, like what is written in the previous line. Can you please just explain once?
Okay. So which step? So how we got from this step to this step, or the previous?
No,
one?
like the typical the cardinality of the typical set.
How we got this?
How we
That's what
got
from this step to this step, right?
Correct.
So by definition, so what? Okay. So let's write it out more carefully. So this is equal to, so I'll just take this out of the summation, okay, because it's independent of Zn. So I have 2 to the minus n times h of z given x times 1 plus epsilon times summation over all Zn such that xn, yn, zn are jointly typical T epsilon of P x y z of 1, right?
Yeah. Yes.
So far so good. Okay, so this is what we have. So this is 2 to the minus n times h of z given x times 1 plus epsilon times the number of, so you're counting 1 for every zn for which xn, yn, zn are jointly typical, right? So it is basically the cardinality of set of all zn such that xn, yn, zn are jointly typical.
So, sir, in lower bound, what we are deriving is we are assuming that x, y, z are jointly typical. Then we are calculating what is the
No.
lower bound set size.
No. So basically, we want to know, we want a lower bound on the probability that x and y and zn are jointly typical, right? So we want a lower bound on this particular probability. So the only sequences of interest for this probability are those sequences which are jointly typical.
Okay.
Right? So that is what we want at this particular point.
Okay.
Right? So if you think about it in terms of this picture, so forget about xn for now because that will just add a little more confusion. So suppose you just have yn and zn, right? So suppose that you pick a particular yn from this particular set. So you know that yn is typical, right? And then you draw a zn which is independent of yn, right? So in that case, so suppose that zn is yn plus, so in this particular case, okay, so in other words, so consider this particular problem where you have an xn, you draw an xn from the typical set, fix any particular xn, but you draw yn independently of xn, okay? But yn is now going to lie in this particular thin shell, right?
Okay.
If you draw yn independently of xn. Now you want to know what is the probability that yn and xn are jointly typical with respect to each other. So in other words, if I draw yn from this shell, what is the probability that it will lie in this particular red region over here? Right? And this particular probability will be very, very small. In fact, the exact probability will be 2 to the minus n times the mutual information between x and y. And that is exactly what the joint typicality lemma is telling us. So if xn is arbitrary, then the upper bound always holds. If xn is typical, then you also have a lower bound. It is at least 2 to the minus n times ixy.
Okay.
Alright. So that is what we have over here. So this part is clear?
Yes, sir. Yes.
Okay. And so we have the size of this set, and this is precisely the conditional typical set of z given x and y. Okay, but do we have a lower bound for this?
Two power n h z given xy.
Correct. 2 to the n
To 1
h.
minus epsilon.
Correct. So it times 1 minus epsilon. Good. So we have this, but what is this equal to? It is 2 to the minus n times h of z given x minus h of z given xy plus epsilon h of z given x plus epsilon h of z given xy. Right? Whatever. So this is 2 to the minus n times. So this quantity h of z given x minus h of z given xy is simply I z y given x plus something, some term which depends on epsilon. Right? As epsilon tends to 0, this quantity also tends to 0 because h of z given x and h of z given xy are both assumed to be finite. So again, we have a lower bound on the probability that all the three sequences are jointly typical. And really, as I mentioned, the right way of interpreting this is in the following way. You have so you should keep this picture in mind. So let us say that I draw an xn from the typical set, which you can say that it's going to be in this yellow region over here, and then if I know that if I draw yn according to py given x, then the probability that they're jointly typical, that is the probability that it lies in this red region, is going to be very large. It's going to be close to 1. But on the other hand, if I draw y independently of x, then it is going to lie somewhere in this blue region. It's going to be almost uniformly distributed in the blue region. And the probability that it lies in this red region is going to be very, very small. So, and the probability that it lies in the red region, that is the probability that it is going to be jointly typical with respect to x, is going to be 2 to the minus, is going to be close to 2 to the minus n times the mutual information between x and y. Okay, and now note that so we have an exponent in terms of the mutual information between x and y, and this will be very important when we derive an upper bound on the probability of error for discrete memoryless channels, because we'll see that the maximum rate that we can achieve, the maximum rate at which we can operate while still driving the probability of error down to 0, will be precisely this particular quantity, which is the mutual information between x and y. Okay. So before we proceed to that, are there any questions? Okay. So really, the only way to get comfortable with all of this is by working it out. You just solve a couple of these problems, find the size of different conditional typical sets and typical sets, and you'll automatically get comfortable with what exactly the exponent should be and so on. And you'll automatically get that intuition. Right? But if you don't work it out, then it can seem very mysterious and can get very confusing very easily. All right. So now let's try to prove. So let us try and prove a lower bound on the probability of error for a discrete memoryless channel. So in particular, we want to prove the achievability part of the channel coding theorem for point-to-point channels. right? So once again, recall we have the problem is the following: we have a message. Let us call it W. So W is a sequence of kn bits. We want to send kn information bits to from through a particular channel. The channel is a discrete memoryless channel. Specified by the conditional probabilities Py given x. We can feed a sequence of length n, let's call it xn, into the channel, and the output of the channel will be another sequence of length n, which we'll call yn. So for example, xn could be, now if the alphabet is allowed to be continuous, then xn could be maybe, if you're fixing the constellation to be QAM or QPSK, then xn corresponds to a sequence of n QPSK symbols or a sequence of n QAM symbols. And the output is going to be a sequence of n real numbers, one for each symbol that is transmitted. Right? Or n real numbers, or n complex numbers, depending on what constellation you use. Okay. So obviously we want to ensure that the message can be decoded reliably. So we do some kind of encoding and decoding. So the encoder basically takes this particular message, which is what we want to ultimately reconstruct at the output, and it converts the encoder or the channel code or the channel encoder takes W, takes the sequence of message bits, and converts it to a code word of length n, which is transmitted across the channel. And the decoder takes the received sequence and outputs an estimate of what the actual message was. So the estimate is also going to be a sequence, a binary sequence of length kn. So each xi comes from some alphabet. So this, if you're fixing a particular constellation, then it could be QAM or QPSK, or if it's just a binary channel, then it could just be 0, 1. So if it's the BSC, then the input alphabet is going to be 0, 1. If it is, say, some QRE channel, then it could be 0, 1, 2 up to Q minus 1, and so on. So this is the input alphabet. Right? So you transmit this through the channel, and at the output you see a sequence of length n, where each symbol belongs to some output alphabet. Right? For example, if you're passing either QAM or QPSK symbols through maybe an AWGN or a fading channel, then the output could be a complex number, or maybe a real number if you're maybe sending BPSK symbols. If for the BSC, so this would be for BSC, the input would be 0, 1. You send a bit, and then you receive one particular bit, which could be flipped with some probability. And maybe if it is a BEC, then the output could be either a 0 or a 1 or an erased symbol. For a QRE channel, again, it could be anything. So in general, this could be maybe you have Q symbols at the input, you have some Q prime symbols at the output. Right? So it's a very general framework where we permit any input alphabet and any output alphabet. But at least for the purpose of this discussion, we will assume that both the input and output alphabets are finite. Okay. So although we can prove the channel coding theorem, we can prove a more general channel coding theorem for for continuous channels as well, we will, at least for simplicity's sake, we will assume that everything is finite. And the main reason for doing so is because all the properties that we have proved about typical sets, in fact, even the definition of the typical set assumes that the alphabets are all finite. Right? For infinite alphabets, it doesn't really make so much sense. So the alphabets are finite. Okay. So this is the assumption. So py given x could be depending on the channel. So for the BSC, we've seen what py given x is. It can be represented, so for any discrete memoryless channel, py given x is the channel transition probabilities, and you can represent this in the form of a channel transition probability matrix, maybe an x by y matrix, where for each symbol, each input symbol and each output symbol, we have py given x of y given x. So essentially all you need to do is specify what the conditional probabilities are, and that completely specifies what the channel is. All right, so that is, so the goal is to design these encoders and decoders, which are going to be functions. So the encoder is a one-to-one function, which maps. Sorry, it could also be a many-to-one function. It's any arbitrary function which takes a particular w and outputs a code word of length n. All right, and generally these will be one-to-one, but we don't enforce it as such. At the same time, the decoder is going to be another function which necessarily has to be which could be a many-to-one function potentially, which maps yn to a particular message symbol w. And so you receive a set of yn, and the goal is to partition the yn space into different regions, which each of which correspond to a particular message sequence. Okay, and the goal is to choose the best encoder and decoder, which ensures that the overall probability of error is as small as possible. But at the same time, you want to make sure that you can transmit a large number of bits over n channel uses. Okay, so in the next class, I'll give a formal proof of the channel coding theorem, which identifies a lower bound on the rate at which you can communicate, such that the probability of error can be driven down to 0. Okay, so we'll stop at this point. If there are any questions, feel free to ask them.
Sir, the reference book which you have suggested, the first one, Network Information Theory, Abbas, that one,
Yes.
It isn't available online, right? The PDF version.
Yeah, so it's not available online. So just give me 1 second.